This is the first lesson of chapter 11, and chapter 11 is all about variable acceleration. Now, I want to just cast your mind back to chapter 9. So when we looked at chapter 9, that was all about constant acceleration. And in chapter 9, that's when we looked at the TBAT formula. Now, that's all nice, and using the TBAT equations is really great for answering questions, but we can only use them for constant acceleration. And in real life, often we aren't just accelerating at a constant rate. We are actually varying our acceleration. So chapter 11 is all about when the acceleration is varying. And if the acceleration of a moving particle is varying, it changes with time. So at time is 0 seconds, the acceleration might be one value, but then a few seconds later, the acceleration might have changed to a different value. And in the same way, velocity and displacement can also be expressed as functions of time. So here we've got some velocity time graphs, and when we've looked at velocity time graphs, such as when we looked at velocity time graphs in chapter 9, we looked at ones where there's only straight lines involved. However, clearly here, we can see they're not just straight lines. And if you remember, back in chapter 9, we said that it was the gradient of a velocity time graph that tells us the acceleration. So acceleration is the gradient of a velocity time graph. And that was nice and easy when we were just doing straight line velocity time graphs. Here, it's just the gradient at any point. So if I want to know the acceleration at this point down here, I just look at the gradient of the curve at that point. So imagine you're drawing a tangent to the curve. The gradient there is my acceleration. So clearly, the gradient of that line that I've just drawn is quite small. It's almost a gradient of 0. So we've got a very small, almost 0 acceleration. If I choose a point later on, such as here, and I draw the gradient to the curve over there, I've got a much bigger gradient, and it's definitely more positive. So I've gone from an acceleration of almost 0 to a much bigger acceleration. So the acceleration is increasing. The gradient is getting bigger and bigger. The acceleration is getting bigger and bigger. This one here, if I look at an early point and look at the acceleration here, looking at a gradient, that wasn't a very straight line, but the acceleration, the gradient is quite big. Yeah, it's definitely positive there. Here, the curve is a lot flatter. If I draw a tangent, again, that's not great. Hopefully that should be touching the curve. Then I've got a much smaller acceleration, a much smaller gradient, so a much smaller acceleration. So I've gone from a bigger acceleration to a smaller acceleration, so the acceleration is decreasing. And that's shown by a curve that is flattening on my velocity time graph. So you can see that the velocity is changing as time goes on, and so is the acceleration. It's changing as time goes on. So we're going to have a look then at example 1. And also I'm actually going to just point out, remember that just like back in the other chapters, we're still going to use an S to represent displacement, a V to represent velocity, and an A to represent acceleration. And we're going to do them as functions of time this time. So, example 1. We've got a body moves in a straight line such that its displacement from a point at a time t seconds is given by S equals 2t cubed minus 3t for t is greater than 0. So all that I'm saying is that as time changes, the displacement's changing with that relationship to the time. And time is always greater than 0. Now that's obvious, we can't have negative time, time's going to be greater than 0. Find S when t equals 2. So find the displacement at time 2 seconds. Well, that's nice and simple because we've been given a formula for displacement. So if I know S is equal to 2t cubed minus 3t, at t equals 2, all I need to do is sub in 2 to this equation. So I'm going to say S is equal to 2 cubed minus 3 times 2. Now, you could probably definitely do this without a calculator, but let's just be safe and make sure we're getting it right. 2 times 2 cubed minus 3 times 2. So at t equals 2, my displacement is equal to 10 meters. Now it says find the time taken for the particle to return to O. So that's the start position. Well, s is equal to 2t cubed minus 3t. If I'm thinking about the particle returning back to the start position, well, that will be when the displacement is equal to 0, because it starts at displacement 0, and if it's going back to the start position, the displacement will be equal to 0. So I'm saying at s equals 0. Well, let's sub that in then and see what we get. So I've gone a bit wonky here, haven't I? Oh dear. There we go. S is 0. So we're going to say 0 is equal to 2t cubed minus 3t. Next, I'm going to factorise. So if I take out factor of t, I get t, open bracket, 2t squared minus 3. Now, clearly, one of my solutions is t is equal to 0. So that's saying that at 0 seconds, we are at the start position. Well, that's obvious. We're looking for the time taken for the particle to return to 0. So that is not my answer. That's just verifying that at t is 0, we are at the start. Well, that's fine. So let's look at then this other bracket. So I've got 2t squared minus 3 is equal to 0. So therefore t squared is equal to 3 over 2. And then t is equal to the square root of 3 over 2. And I'll just do that on my calculator. Square root of 3 over 2 is 1.22 seconds. So the time taken for the particle to return to 0 is 1.22 seconds. That's my answer. Okay, right, let's move on to example 2. Okay, in this example, we've got a toy train travelling along a straight track. So it leaves the start of the track at time t equals 0, and then it returns back to the start of the track at some point later on. The distance, and now that's important that they've said distance there, s metres from the start of the track at time t seconds is modelled by s equals 4t squared minus t cubed, where t is between 0 and 4. And we are being asked to explain this restriction. Now, there's a couple of different ways of doing this. Okay, we can do it using a graph, or we can do it by looking closely at this equation. I'm going to go through both the different ways. Firstly, they've told us that it's the distance, s is the distance and not the displacement this time. That means that s must be greater than or equal to 0, because it's a distance. Remember, displacement can be negative, distance can't be negative because it is a scalar. Distance must be greater than or equal to 0. So, if s must be greater than or equal to 0, that means that this 4t squared minus t cubed must be greater than or equal to 0. Now I can factorise this. I'm going to take t squared out. So I've got t squared brackets 4 minus t greater than or equal to 0. So I want to think about when this is always greater than 0. Now first, if I look at t squared, time is always positive. I can't have negative time, that's just a fact. So t squared will always be positive, and even if I did have negative time, t squared would always be greater than or equal to 0. So if I need this positive thing times this to be greater than 0, then I know that this can't be negative. If I had a positive times a negative, I'd get a negative. Therefore, I need this to be positive. So I know that 4 minus t must be greater than or equal to 0. 4 take away something greater than 0. Well, if I rearrange that, I'm just going to get that t must be less than or equal to 4. And therefore, I've explained my restriction. Well, time has to be greater than 0. It can't be negative. But we've also shown that time must be less than 4. Okay. You would obviously have to write out a bit of an explanation. The examiner probably couldn't tell exactly what you're saying just from this. So let's look at the easier way though, looking at doing it in a graph form. Now, if I want to draw the graph of displacement against time, or sorry, distance actually. Yeah, that's what they told us we're doing, distance. So distance against time. And I know that this is the graph of 4t squared minus t cubed. Well, what kind of graph is this? It's clearly a cubic because I've got t cubed, but not only that, it's a negative cubic, so a negative cubic graph. And I know that negative cubic graphs, oh, that's not a very good drawing, but you get the idea, they go like that. And so I want to know where my roots are. Well, actually, it's quite handy that we factorised over here. I can quickly see what my roots of my equation are. This should be quite similar to what you've been doing in core maths. Well, here I've got a repeated root of t equals 0. So I know we're going through t equals 0. The other root is t is equal to 4 over here. So if I sketch my graph, I go down, I've got my repeated root here. Then I go through, t is 4, and back down. So that's 0, that one's 4. So that's my graph of the distance against the time. Now, remember we said that distance must be positive. Well, the only section on this graph where distance is positive is this higher section here. Anything after t is 4 is negative, so we definitely can't include that section. We also know that t itself can't be negative. We can't have negative time. So the only valid section of the graph is actually this bit here. And that valid section is where t is between 4 and 0. So if I just explain that, that's because S must be positive, so it must be above the t-axis, and also t cannot be negative. So we must be looking to the right of the s-axis. And that means that we can only be considering this valid section here. T is between 0 and 4. Okay, final example then is this one here, example 3. Let me just focus that. Okay, so a body moves in a straight line such that its velocity at t seconds is given by this formula here, which is a quadratic graph. And for t is greater than or equal to 0, we know that time must be positive. This time we've been given a formula for velocity, unlike the others where we were given a formula for distance or displacement, but that's fine. The first thing says find the initial velocity. Well, clearly, initial means at the start, so I'm just looking for the velocity when t is equal to 0. So let's sub that straight in. The velocity when t is 0, well, I've got 2 times 0 squared minus, sorry, that went a bit wild, 16 times 0, 16t, and then plus 24. Well, quite clearly, my initial velocity then is just 24 meters per second. Then the next one says, find the values of t when the body is instantaneously at rest. Well, what we mean by instantaneously at rest is when the velocity is equal to 0. So when velocity is equal to 0. So let's put that in. Instead of v, we're going to have 0. 0 is equal to 2t squared minus 16t plus 24. Now, you could obviously do this straight on your calculator. I'm going to start off by dividing by 2. 0 is t squared minus 8t plus 12. And then, let's see, I can factorise this. Obviously, I would probably check this on my calculator in an exam just to make sure I've definitely done it right. So I'm looking for multiplying to make positive 12, so I'm adding to make minus 8, so minus 6 and minus 2. And so at t equals 6 seconds, and at t equals 2 seconds, my velocity will be equal to 0. So those are my two solutions, 2 and 6. Part C, the value of t when the velocity is 64 meters per second. Well, again, let's just sub in v is equal to 64 meters per second. So 64 equals 2t squared minus 16t plus 24. Let's take that 64 to the other side. So we get 0 is 2t squared minus 16t minus 64, so minus 40. I'm going to divide by 2 again, so I get t squared minus 8t minus 20. So I'm looking for multiplying to make minus 20 and adding to make minus 8. Well, I've got t plus 10 and t minus 2. Oh no, that's not right, is it? Sorry, wrong way around. T plus 2 and t minus 10. So my solutions then are t is equal to 10 seconds or t is equal to minus 2 seconds. Now, quite clearly, we can't have negative time. We were told that t must be greater than or equal to 0, so this one is not a solution. We can ignore that. This is my only answer. At t is 10 seconds, the velocity will be equal to 64. And finally, D is asking for the greatest speed of the body between 0 and 5 seconds. Now I'm going to do this by looking at a graph of the velocity against the time. I could do this using differentiation to help me. I'm not going to, but we're going to see later on in the chapter how we use differentiation to solve questions like this. So I know that the velocity is equal to 2t squared minus 16t plus 24. This is a quadratic and it's a positive quadratic graph. There we go. So if I draw this graph, I know that it goes through v is 24. Quite clearly at the end we've got 24, and actually we worked that out in part A, that when t is 0, v is 24. I also know the roots, because we worked them out in part B, that at t is equal to 2 seconds and t is equal to 6 seconds, it goes through velocity 0. So if I try and draw on this, it's a positive quadratic, so that's the smiley face graph. There. Now, I don't know if I've drawn that accurately. You know, it could go a lot further down here than I've drawn. So, it's finding the greatest speed of the body in the interval t is between 0 and 5. Now, 24 looks like it could be a contender because at t is 0, the velocity is 24. However, I need to check that the velocity it gets to down here is no lower than negative 24 before I make my answer. So what I'm really saying is I need to find the velocity at this minimum point here. Now, I could use differentiation. We know how we use differentiation to find a minimum point. Instead, I'm just going to use the fact that quadratics have a line of symmetry. So I know here, at the time t is 4, because it's halfway between 2 and 6, if I just work out what the velocity is at t is equal to 4, that will tell me this minimum velocity down here. I'm running out of space a little bit. I'm going to do it on a post-it note at the bottom. So here we go. So at t is equal to 4, the velocity is equal to 2 lots of 4 squared. Remember, all I'm doing here is plugging into my formula for velocity. 2 lots of 4 squared minus 16 lots of 4 plus 24. And let's see what I get for that one. 2 times 4 squared minus 16 times 4 plus 24. And I get the velocity is minus 8 meters per second squared. Oh, meters per second, sorry. So what I'm saying is down here, I get to negative 8. Well, clearly that speed, 8 meters per second in a speed, because remember speed is scalar, is not as big as 24. So between time is 0 and time is 5, the greatest speed is going to be 24. So let's write that on my post-it note. Greatest speed in interval, in the interval 0 to 5 seconds is 24 meters per second. So all I said then is in this section from t is 0 to t is 5, the biggest speed that we reach is 24 meters per second. Okay, now we've done those 3 examples, you should be able to have a go at exercise 11A.